Okay. Okay, let's do a quick review. What did we do last time? A lot. But one of the things we did is at the very end of lecture, we looked at this thing called arc length. And I claim you already learned it, or at least the two-dimensional version of this arc length formula in Calc 2, when you studied the parametric equations at the last week of class, when you took Calculus 2. And so you learned this arc length formula, and we just jacked it up one level to accommodate a three-dimensional curve. And so you just, you have the h prime of t squared underneath the radical also. That's all. So a quick reminder is that arc length is merely the integral of speed, where speed is the magnitude of your velocity vector. And that's still true. It's true in Calc 2, although they didn't frame it up that way. And it's true here. So we did a couple examples, and I would encourage you to make sure you study and do your homework, because this is going to be on the quiz Sunday morning. And so is this stuff, arc length function. What the heck is an arc length function? Yee. Okay, so let's start off with some motivation. Do you recall that when we learned how to come up with the parametric equations for a line, that I told you they're not unique, that these equations for the line might be like, you might have a different answer than me, but we're both right. And the reason why is because your direction vector with the direction numbers A, B, C might be multiples of mine or something like that, because it's just parallel. Or the coordinates of the point that you chose that lives on the line is different from the point that I chose to live on the line. So that it may be different parametric equations, but still, we're still describing the same identical line in space. So what of it? Well, it turns out there's even more parameterizations. Oh my God, really? Than the ones that I just told you about. Okay. So take a look at this weird example. It turns out that this parameterization, R of t equals t squared, t cubed, and it's what we call a twisted cubic, is exactly going to give you the same curve with this. R of u equals e to the u, e to the 2u, e to the 3u. So u is the parameter now. Only the range is different. So here, this was the curve, the twisted cubic. By the way, the twisted cubic looks kind of like that or something. I'll graph it for you in a second. But we're only going from 1 second to 2 seconds. So it's only taking a little portion of the curve. And then the same portion of the curve if you start u at 0 and go to ln of 2 for this parameterization. So there's a brand new parameterization, but they both give you the same thing. So if I were to prove this to you, let's see if I can come up with let's see here, 3 vector. Make sure I get my keyboard ready to rock. Equals, this is really cool software. I think I showed this to you before. Equals, let me move this down, equals another 3 vector. So this is how you do vector valued functions here. So if I just put in t squared, whoops, that didn't work so well. Come on, baby. Get rid of that y. No. It's a little grouchy this morning. Yeah. And then instead of z here, we'll have z equals t cubed. And if I try graphing it now, I may only graph a little piece of it. Yeah, this is a little piece of this twisted cubic. So let me have t go from, they want us to have t go from 1 to 2. That's going to be just a really small piece of it. Not much. So if I, oops, that did not let me change it. Let's try that. Okay, so it's giving me a piece of this twisted cubic. I think you could see it right there. Ooh, I'm getting a little seasick with it all rotating all over the place. Good God, man, stop. Okay, so there's a piece of it. Now, this is kind of like, I don't like usually graphing little pieces of curves. I'm going to just go from t going from negative 10 seconds to positive 10 seconds. Let's see what happens now. Just so you can see a little bit more of the picture. Whoa, see how there's a twisty in it? It's a little twisty. That's the twisted cubic. Pretty cool, huh? Nice. So what if we graph the other parameterization of it? So what if I have e to the t, and they're just using u as a dummy variable there, so it doesn't, oh, come on. So here I'll go e to the, what was it, 2t, and then here I'll go, no, come on. there we go, e to the 3t. Now there is a difference between these parameterizations, because this parameterization, exponentials never go negative. They never do. And so some of you blew that on midterm 1, where I think I was asking you about domain of a vector valued function. And I think it was e to the t plus 1 or something. And you said, oh, as long as t plus 1 doesn't equal, I don't know what you said. But look, there were no restrictions on the domain for that component, because exponentials will never go negative. So here, if I do graph it, whoa, and we have weirdness here. So let me try the 0 to ln of 2. Nope. Can I do ln of 2? No, what is ln of 2? Hang on, I have to do a number here. ln of 2 is like, I think it's 0.693. I'll just go to 1. It's good enough for government work. Okay, let's just see a piece of it. So this piece here looks the same as that piece from the other parameterization when we were going from 1 second to 2 seconds. So they're identical, at least on a portion of the curve. So I just wanted to show you that. And so what of it? How can you get other parameterizations? Well, one way is to use this really cool idea called the arc length parameter. It gives you access to come up with a different parameterization. So let's look at the arc length function next. So what the heck? Yeah. All right. So the arc length function looks like the arc length formula. You're like, what's the difference? This looks like the arc length formula. True. But notice the limit here is a variable instead of a pure number, and same with this limit. Although typically the lower limit is 0. Most of the time you can assume this, but not always. You have to be a little bit careful, because you may not get to say it's the lower limit is 0. Be careful on a quiz problem. That's a hint. And so if I write it as speed, whoops, not a double integral, it would look like this, a to t, and then we would have r prime of u du. Since we already used up the t for the limit, we're using the dummy variable of u in the integral. Okay, so what about this arc length function? 2 cool facts. Okay, so here's the arc length function. It is a function. In other words, s of t is going to equal that integral. Okay. Using the fundamental theorem of calculus, it turns out if you take the derivative with respect to t of this integral, and you guys remember when you take the derivative of an integral, derivatives and integrals are inverse operations of each other, so you'll just end up with what's inside the integrand. So you'll basically get your v of t, which is the same as the first derivative of your position function. Same thing. Now, here's the other cool fact. This is really weird. You probably don't buy it, but it's true. If your magnitude of speed is 1, and that's rare, but if it is, because usually it's some scalar function of t, if it is equal to 1, then when you do this arc length function, that means, oh, I'm just integrating 1 with respect to u. Okay, well, that's just going to give me u. And then if I evaluate between the limits, I get this. And if this is 0, which a lot of times it is, then you'll get just t. And so the cool thing is your s function is exactly the same as your parameter t. So this is a way to tell if your parameterization is the arc length function. Okay, so let's move on and just do some cute examples, and you'll do this in the homework too. So I'm just going to walk you through how you do these problems. Okay, so here's a position function. R of t is 2t, 3 sine 2t, 3 cos 2t. And we did this problem already in a previous example. We found the arc length for it. So if you don't believe me, you can go back to one of the problems we found an arc length for. Where the heck is it? Not that one. I think it was this one right here, example 4. Remember we did that one? So there's the very same position function. I'm just repeating it. And so we already found the arc length on a certain interval. So we're basically, we did that, and then we found that the speed was a constant. So there's that. So I don't want to reinvent the wheel for this new example. So let's just use what we already kind of have. So if I use their definition, the definition is the integral between the limits of a to t of magnitude of r prime of u du, but we found, and we're going to use the lower limit being 0. That's tradition a lot of times. And we found that the speed was just a constant. And it's like, oh, okay. And now if we integrate that with respect to u, okay, but that's just going to give me 2 square root of 10 u going from 0 to t, but then that's just going to be 2 square root of 10 t. Okay, fine. So what are we saying right now? We're saying s of t, which is a function now, function of time t, is 2 square root of 10 t. Put a box around that. That's your key. That's your answer for letter A. And that's your answer for letter A. Now what? We're going to use this arc length function to re-parameterize the curve. This curve right here is parameterized using t, but what if we re-parameterize it using this arc length s for the parameter instead of t? Well, how the heck are we going to do that? You're going to take this answer you got from part A, and you're going to solve for t, which is pretty easy because you just, where this side is just an s. So if I just divide both sides of the formula or equation by 2 square root of 10, I have that. Then what? You're going to substitute this into r of t for t. So what am I saying? See, if you look at the position function they gave you, here it is. And everywhere you see a t, there's a place, there's a place, there's a place. I see 3 of them there in those components. You're going to substitute s divided by 2 square root of 10 instead. So here we go. So r re-parameterized using s, this arc length function, is going to be 2t, but that's going to be s over 2 square root of 10, comma 3 sine 2t, but that's 2 times s over 2 square root of 10, comma 3 cos 2t, but that's really going to be 3 cos 2 s over 2 square root of 10. And then clean this up a little bit because, you know, I dock you a point unless you reduce things to lowest terms. And so you can finish up part B here, making it look a little prettier. S over square root of 10, 3 sine s, 3 cos. Uh-oh, my internet's giving me an error message. I'm unstable. Can you guys hear me okay?
It's kind of choppy.
Yeah, you're just cutting off right now.
Okay, hang on a minute. That tells me that I need to get rid of some crap. Sometimes, see if this helps. Does this help a little bit? Any better?
Yeah, it sounds better.
A little better? Okay. Sometimes if I have too many tabs up, it slows down the poor computer. It gets overworked. Can't handle Zoom at the same time. Zoom apparently uses up a lot of memory. Let's choose it up. Okay. Now that we have our answer to letter B, so this is our answer for letter B. Yay, we re-parameterized it. Is this the same curve as the original? Absolutely. It's a different parameter. Now, if I were graphing it, the range might be different. As you saw in that one example, the range for parameterizing with the t, if I want the curves to match, was like 1 second to 2 seconds. And when I parameterize it with that other parameter u, it was like 0 to ln of 2 or something like that. So they essentially graph the same thing on certain things. Okay, so now what? So we want to just prove one of these cool facts is true. So let me go back here. This was one of the cool facts. So is it true? So we're going to see if it is. So letter C is show that this r prime of s equals 1. Well, okay. So here's r of s. If we get the derivative of that, r prime of s, and you guys know how to take derivatives of vector valued functions because you had to do that on the midterm. So the first component, the derivative with respect to s, of course, is of s over square root of 10 is just 1 over square root of 10. And then when we differentiate the sine component, for the middle component, I'm going to have, using the chain rule, 3 over square root of 10 cos s over square root of 10. Okay, lovely. And then the last component, we're differentiating cos. You know that's going to be a negative sign, so I'll have negative 3 over square root of 10 times sine s over square root of 10, like so. Okay, now what? Now go get speed. That's the magnitude of this derivative. And you know you're going to take the square root of yuck. The sum of the squares of the components. Oh my goodness, this is going to be kind of messy, but we know it's going to work out a little bit nice. All these. Okay, so look at that yucky radical. Can we simplify it a little bit? Well, yeah. So if I look and start squaring all of the terms underneath the radical, I'll get 1/10 for the first term. Now, the second and third terms have something in common. They both have 3 squared, which is 9, over square root of 10 squared, which is 10, 9/10, as a common factor. So if we factor out the 9/10 from those last 2 terms, we end up with the other factor, which is a cos squared plus a sine squared, which you guys know is equal to
1.
1.
1.
Yay! And then what do we have? We have 1/10 plus 9/10. Last time I checked, that's 10/10. But that simplifies to 1, and then the square root of 1 is 1. And so one of the cool facts that we showed is really true, that if you parameterize your curve with the arc length parameter, it has a really cool property. Speed will always be a 1. So that's a nice test. If somebody says, oh, did you use the arc length parameter, even though they may have replaced all the S's with different letters like G's or something, is that the arc length parameter or not? And if you test it by finding out if speed is equal to 1, then it is parameterized using the arc length parameter. Now, for those of you who think, oh, this parameterization is just like bunk, no, it's not. It's like really used in a lot of mathematics. I mean, when I did my master's degree many years ago, my whole thesis was on parameterization. Really? Yeah, I was parameterizing an infinite curve called a Van Cook snowflake curve. It's a fractal, which is like crazy. It's nowhere differentiable. The arc length is infinity, but there was a way to parameterize it. It was really, really interesting too. If you want to, I wish we were face to face. I could show it to you. But anyway, we may not be going back to face for another year, I heard through the grapevine yesterday. So, all right. So now let's keep going. So where on this curve, I'm up to letter D now, where on this curve are we if we went a distance of pi square root of 10/3? So if you started off at like t equals 0, say, and you were, by the way, I think this curve is a helix, so it looks something like this. Woo, yikes, that's fun. So let's say you started at t equals 0, which I think is at the point 0, 0, 3, 0, 0, 3, which would be something like, I don't know, like right here, I'm just guessing. So 0, 0, 3 would be where time t equals 0. And you traveled a certain distance. So you're like, oh, I'm, just going, humming along this curve. So you start going along the curve. Let's say you make it over to here. I'm just guessing, like right there. And let's say that length, that arc length, is this number, pi square root of 10/3. Okay. Where are you on the curve? Like what are the coordinates of the point right there? Like you made it, like woohoo. So what you're saying here is you're saying the arc length, which is we always say is S, also the way to denote arc length parameter, is pi square root of 10/3. That's how far along the curve you went. So great. So now what? Well, you know that S, since we already know that S, when we found the arc length function, S of t, S was equal to what? 2 square root of 10t also. So this S here had better be equal to this S there. So you basically equate these two S's because S has to be equal to S himself. So you're like, oh, pi square root of 10 over 3 has to equal 2 square root of 10t. And then solve this for t, and you'll know what time it is on your watch that you ended up over here at this point, you know, the ending point. Okay, so if I divide both sides by square root of 10 and also divide both sides by 2, I'll have time t equals pi 6 seconds. And then substitute this into your position function, your original r of t, and you're going to go, oh, okay, r evaluated at pi 6 seconds, and that's going to give you the coordinates on the curve. So you'll go 2 times t pi 6, and then you'll have 3 sine 2 times pi 6, and then you'll have 3 cos 2 times pi 6, like this. And, you know, before you actually go look up your trig circle, you want to reduce 2 over 6 reduces to thirds here. So, you know, do you remember what sine of pi thirds is? Yee. Or how about cos of pi thirds? Yee. And here you'll reduce 2 times pi 6, which reduces to pi thirds. So I get pi thirds, and then I think, let's see, sine of pi thirds, I think, is square root of 3 halves, and cos of pi thirds, I think, is a half. And folks, this is the position on your curve when you stop, you know, walking along the curve and made it a distance of pi square root of 10 thirds. So this is the point's coordinates. So that's it. You're done. That's the point's coordinates. It'll be the tip of your vector. Okay. So somebody says, give me the point. Well, then you'd have to use parentheses. So the coordinates of the point that you finished would be this. Now remember, there is a difference between a point, we use curvy parentheses notation, and a vector, we use angular brackets in this class. Now, if you're taking linear algebra right now, I apologize, but they may be using this other book where they denote vectors using parentheses, which is annoying because then there's no way to make a distinction between vectors and points, which is ridiculous. But whatever, I don't make this stuff up. I just report it. Now let's do a true or false question. True or false? The curve, big R of t, with these components t squared, 3t squared, is parameterized by arc length. True or false? How would you test it? Based on this whole page of what we did here.
It's true.
Okay, do you remember that one of the cool facts from this theorem over here? This is the test to see if it's parameterized using the arc length, okay? So you have to test it first. You can't just look at it and go, yes, it is. That's not going to cut it. So we have to do some work here. This is the test. Before we can even say true or false. So let's do that. So the question is, in order to answer letter E here, let me append a page, is the magnitude of r prime, basically the speed, is that equal to 1? I don't know. So is magnitude of big R prime equal to 1? If yes, then yes, it's parameterized by arc length. If no, then it's not. Okay, so let's go get R prime first because they gave us the big R. Okay, get his derivative. Well, the derivative of t is 1, derivative of t squared is 2t, derivative of 3t squared is 6t. Okay. Now let's go get that magnitude of velocity, which is the same as speed, square root of the sum of the squares. Now, without even simplifying this radical, is this going to equal the square root of 1, which is 1? Yes or no?
No.
No. So the answer to this true or false is false. It is not parameterized by arc length. Okay. So we're done with letter E. That's the quick trick. Okay.
Can you scroll down just a little bit, Professor?
I sure can.
Cool. Thank you.
You're welcome. Okay, any other questions? Hey, Nathaniel, real quick, you're not in trouble or anything. I just wanted to ask you a quick question after class. Just take me 5 seconds. If you could stay after class real quick, would appreciate it.
Yeah.
Yay, okay. Good to know. All right.
So, Professor, if that was like a quiz or exam, we would just show it by doing the taking the magnitude.
Yep. That's the quick trick. That's the quick trick to see if it was parameterized using the arc length function or not. Yep. Now, folks, when something is parameterized using the arc length parameter, it's rare. I mean, you're not going to see that all the time. It's a very special parameterization among a million different kinds of parameterizations, because parameterization is not unique. There's all kinds of wacky ways to parameterize something, just so long as it matches your curve. You know, it can't be some other curve. You know, well, it's parameterizing the same curve. It's like, well, they're not identical curves, so yours doesn't work. But there are different ways. You can parameterize a straight line using its slope. There's all kinds of wacky stuff. And like I said, my thesis was weird.
Well, I'm sorry. What was the magnitude for the r prime of t?
It's just this wacky radical. It's this, which is like a scalar function of t. You know, I mean, if I cleaned it up and made it look kind of pretty, which, you know, it's not that good, it would look like this. That's a 40. Square root of 1 plus 40 t squared, okay? And that's definitely not equal to 1. Do you get that?
Yeah.
Definitely not. It's just a weird scalar function of t. Okay, now we're done talking about arc length and arc length parameter. New topic, but it involves arc length a little bit, okay? We'll finish out chapter 14 and discuss curvature. Believe it or not, there's a way to measure how curvy a curve is, which is kind of cool. You know, so if you've got like curly hair, we can actually measure how curly your hair is. That's kind of a unique thing, you know? It's like, wow, that's interesting. So if you want to see this really cool application of things that we've learned so far, especially with the unit tangent vector and that kind of junk, here is an application of it. Like, why do we even have to learn about this weird stuff? Because there's applications. It's great. I love this stuff. I love it. I mean, if you're not having fun in my class right now, you're not doing it right, okay? I know it's early and you're tired, but grab a cup of coffee and join me here. This is awesome. Okay, how to find curvature or measure curvature. I hope you can appreciate that some things are more curvy than others. I mean, a straight line has zero curve to it, right? Because it's straight. Like if you have straight hair, there's no curve to it. Your curvature would be measured as 0. And that's, we'll even prove that. Now, you know, other things could be more curvy than others and so on. So how do you measure it? Like, how do you quantify it? And that's the cool thing. And that's where arc length parameter S gets into the conversation, which is kind of neat. It helps you measure how sharply a curve bends. For instance, take a look at this little diagram here. Would you agree that if you sat over here at point P, the curve is more curvy here than it is if you were located over here at Q? Over here at Q, it's almost straight, not exactly a straight line, but the curvature over there at Q would definitely be measured at something less than the curvature over here at P. So what? Well, what we're going to do is the way we're going to figure out this curvature measurement is we're basically going to look at how fast the unit tangent vector is changing his direction as you move along the curve. So what the heck? Remember, the unit tangent vector is just the unitized velocity vector. And it's the derivative of the position function. So if this is a picture of R of t, this curve here, you know, and it's like a little fly flying around like this, then at any point, if I were to sketch the unit tangent vector on this curve, I'd sketch a whole bunch of them. Like over here, remember the velocity vector is tangent to the curve. So if we just, you know, these little unit tangent vectors, there's one, there's one, there's one, there's one, more. I'm trying to draw little tangent vectors to the curve. So there's a whole collection there of little unit tangent vectors t. So those are collections of t's. Now, here's the key. Look over here where it's really curvy, the point P. It's super curvy over there. Do you notice these unit tangent vectors are changing direction? You know, first they're sort of pointing to the left, and then they're pointing a little bit more up. And then right here at the vertex, it's pointing straight up. And if I just took the tangent vector right there at that vertex, it's pointing straight up. And then it turns around and starts pointing to the right as you traverse the curve. So it's changing more rapidly here than it's changing over at Q. Over here at Q, it doesn't look like the little unit tangent vectors are changing direction much at all. They're still pretty much pointing to the right and so on. So here they're changing fast, and over here, not so much. So what we're going to do, this is how you calculate curvature. You calculate the magnitude of the rate of change of the unit tangent vector with respect to the arc length, you know, as you're traversing around a piece of the arc. So I'm going to give you several curvature formulas, okay? So one of the curvature formulas, which relates to the arc length parameter, is if you have your curve already parameterized by the arc length parameter, so you're given R of S, and you know for a fact it's parameterized using the arc length function, then you can measure your curvature by finding big T prime of S, magnitude. Okay, which is, you might see it in some books like this, same thing, okay? Where the unit tangent vector, which you have to get first, is just the unitized velocity vector as before, except that you're using the S for the parameter instead of T. So this is one of the curvature formulas you can use. Although on most of my quizzes and exams, since it's so rare to have your function parameterized by S, I usually never get an opportunity to use this formula. So I'll just put not common. So which formulas are we going to use? I'm going to give you the ones that are more typical of what you'll use on quizzes and exams. And here are 3 more of them. Oh my God, 3? Don't worry, I'm not asking you to memorize. You know, I let you use your notes when you take quizzes and exams. Thank goodness. If we were face to face, I do let you have a formula sheet. So this one is my personal favorite. I love this one. The magnitude of big T prime divided by speed, the magnitude of R prime. Although sometimes that one is a pain in the rear end to get because T prime has you doing like the quotient rule and the chain rule, and it can be a nightmare. And when that happens, then I use this one. It's not as bad. I try to avoid this one mainly because cross product of the velocity with acceleration and then taking the magnitude of that is open to a lot of silly mistakes. Anytime I take a cross product, and some of you found out, if you copy down one of the components wrong or you forget a negative, your whole cross product goes down the toilet. It's really frustrating. So I usually don't use that one unless, you know, I'm up against a wall. This one only works for 2D, and it's a very special 2D. You have to have your position function, if you will, not a vector valued function. It's just a function of X. And you can find curvature that way. Not as versatile formula. Okay, let's go do some curvature problems. And that'll wrap us up for today. And if we have any extra time today, I'll be happy to go over any midterm solution keys, but I still have to do examples 7, 8, 9, and 10, and maybe a little bit about A sub t and A sub n. Okay, so we're going to prove that lines have 0 curvature. Now, that's kind of like, why do we have to do that? That's kind of silly. It's obvious that a straight line doesn't have any curvature. But I want you to see that this formula really works. That's why I kind of want to show you this really easy problem that's kind of, you know, Captain Obvious here. So here's what look like parametric equations for a curve that somebody just stuck inside of a vector valued function. Yeah, so if you did graph it, it would be a straight line. Fine. Now, if we're going to use the curvature formula, and I'm going to use this one right here, K is traditionally used for curvature. We're going to use K is the magnitude of big T prime divided by speed, which is the magnitude of your velocity vector. So we're going to use this, and it's going to turn out that that's going to be 0. Really? Yeah, well, show it. Okay, we got to get all the ingredients. So first up, you're going to get the derivative r prime, and it turns out this is really easy, and it's just going to be a constant vector. That doesn't always happen, but hey. Then what? Well, you need to unitize that to get big T. So you're going to go, all right, well, I'm going to need the magnitude in order to unitize. So what the heck is 1 squared plus 2 squared plus 7 squared? Well, 1 plus 4 plus 49. I think it's square root of 54. And let's simplify that radical a little bit, because I think 9 times 6 is 54. And 9 is a perfect square. So when we simplify the radical, it's 3 square root of 6. So now your big T, which is just r prime unitized, is going to be -127 divided by 3 square root of 6. And so when I distribute my scalar, I got this mess right here, and no need to rationalize the denominator. So there's big T, fine. Now go get big T prime, because that's what's in, that's the part of the numerator of your K curvature. Well, the magnitude of it. So big T prime, when you take the derivative of big T, well, oh my goodness, big T is all constants. so it turns out that big T prime is the 0 vector. Oh my goodness. So what does that mean? Well, then the magnitude of big T prime, I hope this is pretty obvious to you, you know, what's the square root of 0? 0. And so now when you put this all together, you go K is going to be the magnitude of T prime, 0, over speed, which we got is 3 square root of 6. I hope you get that that really is a 0. And that's exactly what should happen. And so the formula works, and we win the game. Questions? You're not going to have something like this on a quiz or exam. I just wanted you to see that this does do the job.
Looks good.
Looks good. All right. Now let's talk about circles and how curvy circles are. So before I do this problem, I want to put 2 circles up here. So here's a tiny circle. Eek. And here's a big circle. I know those are sad looking circles, but try to use your imagination. Now this circle has, let's say, a tiny radius, and this circle has a much larger radius, right? So we'll call that R1, and this is R2. The question I have for you is, which one of these circles do you think is curvier than the other, or do you think they have equal curvature?
Can we tell just by looking at it?
Well, yeah, this might help you. Pretend you're in your car and you're driving around one of the circles. Let's say you're right here and you're driving around the circle. Like zzz. And let's say this is another road on the tinier circle, and you're driving around this circle. Would you have to crank your steering wheel a little bit harder in order to navigate one circle over the other circle?
Yeah.
Yes.
Yes, you would. Which circle would require you to really crank that steering wheel a little bit more?
The
Smaller one.
Yeah, this is more curvy. He has more curve than the larger circle. You see, the larger circle, if you're driving around like a big, I don't know if you've ever done like an off ramp or a circular thing, you don't really have to, you know, it's almost, it's not really straight, but it's not that curvy here because it's such a large circle. So the larger the circle is, the less curvy it is. And the tinier it is, the more curvy. And that's the point. So circles do have different curvature, and it's inversely related to its radius. The tinier the radius, the more curvy it is. So we're going to show that curvature has an inverse operation to the radius, because the radius here is in the denominator. It's not a direct proportion, it's an inverse proportion. So if the radius goes down, that denominator is tinier, and tinier denominators lead to larger quotients, and vice versa. Okay, so let's just check it out. here is a parameterization of a generic circle with radius r. So if you don't believe me, plug in r equals 2, whip out your calculator and graph in parametric mode, of course, 2 cos, 2 sine, and you'll get like a little circle of radius 2 centered at the origin. So r is just going to be some radius. So to get the curvature formula, we're going to go ahead and use the same formula as I did in example 7. So we're going to need to go get big T prime. So that means we're going to need to go get big T first. So I go get the velocity vector, the derivative, r prime, and then I need to unitize it. So I'm going to have to figure out the magnitude of that. And you know what we're going to do. We're going to pull out a common factor of r squared. And it's a beautiful thing because you can use that trig identity. Sine squared plus cos squared is 1. And then, ooh, we're just taking square root of r squared. And we get the absolute value of r. And it's definitely going to be something positive. Otherwise, we have an impossible circle. Okay, now what? Well, we're going to put the unit tangent vector together because that's what we're on track here. So you're going to go, all right, here's my velocity vector, and I'll divide by the magnitude. Hey, and the r's cancel. Woohoo! So I get this for my unit tangent vector, negative sine t cos t. Then what? Not ready yet, because look at the curvature formula. It says I need the magnitude of big T prime. Okay, so you got to keep going. So big T prime is going to be a vector with components. Let's see, what's the derivative of negative sine? I think that's negative cos. And then the derivative of cos is negative sine. Great. And now you're ready because your k, which is the formula magnitude of big T prime divided by speed. We already got speed. Remember, it's r. So you're like, okay, it's up here. So you're like, okay, I know that denominator. But then I just got big T prime. So let's go ahead and get his magnitude by taking the square root of the sum of the squares. But hey, cos squared plus sine squared is 1. So we just have square root of 1 over r, but that's 1 over r. We're done. And this is curvature for any circle. Any circle you hand over to me, I can give you the curvature right away as long as I measure off the radius. And we're done. Cool beans. Questions so far? These are classic. Go ahead.
When there's questions like this, can we just use 1 over r, or do we have to show all of the work?
Well, now that you know what a circle's curvature is, you don't have to do all the work, but the odds are I'm not going to ask you for the curvature of a circle on a quiz or exam, because, then you don't have to do any work. Why would I do that? Yeah, you're probably going to have something a little more involved. Yeah. Okay, so let's look at another one. Anytime you're asked to do a curvature problem, do it from scratch. I basically want to see you follow the procedure of getting your big T and your big T prime. And, it's just a nice procedure. It's not that hard because you don't really have to think hard to set it up like some problems can be in this class. Like as some of you saw, some of you got a little weirded out by that vector problem on the midterm because it was involving 3 vectors, with winds and then velocity had to be figured out. So some people did that in a very strange way. I don't know. And then the projection problem, well, we'll talk about it if we have time. Okay, let's talk about curvature of a helix. This is a generic helix where a and b are positive numbers, a cos, a sine, bt. And if I were to sketch it with some a or b values, it's going to look like that. Oops, like a slinky here. Woo, like that. So that's, and I hope that you can see that it does look like the curvature is going to be constant no matter where you are on that helix. Okay, well, let's prove it. What kind of constants? It's not what you think. So we got to go through the work. So I'm going to get r prime. I'm going to go kind of fast now. Okay, derivative of a cos is negative a sine. And then the a cos is the derivative of the middle guy, and then b. Okay, let's go get the magnitude of that. And then here, if you factor out an a squared, like we've always done before, you'll have the other factor be sine squared plus cos squared, which is 1. And so this is just going to end up being the square root of a squared plus b squared. Fine. Therefore, your unit tangent vector is going to be the unitized derivative. It's a positive. A cos all over this magnitude. And then the b all over the magnitude. Okay. And now you got to go get big T prime. Okay. All right. Derivative of minus a sine is minus a cos. And these multiples stay there. Derivative of a cos is negative sine. So we've got negative a sine t all over square root of a squared plus b squared. And then, hey, this is a constant. And what is the derivative of a constant?
0.
Thank you. Awesome. So then what? Well, that makes it a little easier to find big T prime's magnitude because we have one less component to, put under the radical. So you're going to have, here you have a cos t all over square root of a squared plus b squared. And this will be a sine t all over square root of a squared plus b squared. And then what? Well, after you do all the cleanup here, you have two fractions here that have the same denominator. And when you square a square root, the radical disappears. So you really have one quotient. That's a t. Oh, bummer. What just happened? Oh, here we go. That's a t and then plus a squared sine. My t's look like plus signs. It's awful. But then my 4's look like 9s and my s's look like 5s, so I can't read my own writing. It's a nightmare. Yeah, so in the numerator, when you factor out an a squared, you get the cos squared plus sine squared factor again, which is 1. So this just ends up being, square root of a squared over a squared plus b squared. But then you can use a law of radicals, which says the radical of a quotient is the same as a quotient of radicals, which is a nice little thing. Of course, everything has to be positive for you to use that. And now we're almost done. Your k is the magnitude of t prime divided by speed. So we just got the magnitude of big T prime. That's our numerator. So you're like, oh, okay. So you've got a over square root of a squared plus b squared. And you're going to divide that by, what the heck was speed? I forget. Oh, here it is. The square root of a squared plus b squared. And then you can clean this the mess up because I don't like fractions inside of fractions. And after simplifying, by turning this division problem into a multiply problem, you'll get a over a squared plus b squared. And that is a constant. So in this case, not always, you again have a constant curvature for helix curves. That's kind of neat. And yeah, I know a lot of this is very formulaic and tedious. And I'm sorry. So, it's time for a meme because, we're all tired. You know what I mean? Like, I'm really tired. So, feels like Friday, doesn't it? Yeah. Let's do, I need to go find my mail for a second. Let me just go get that real quick. Oh, why? Hang on a second. Why is this no longer one of my most visited sites? I don't know. Here it is. Okay. I found it. You'll love this, especially if you've been looking forward to ending the pandemic. I don't know. It's loading. Oh, I know. It's not. Let's try something else. That's really weird. I'm going to have to re-download it. Okay. Okay, finally. All right, let me go share this with you. I think you'll appreciate a little smile. We could all use one today. So I found this comic in a paper a couple days ago. I know you guys probably don't read an actual hard copy newspaper, but I do. You know why? Because Zeke needs to read yesterday's newspaper on the bottom of his cage. Here you go. The clothing stages of a pandemic. Stage 1. Sweats are okay for work Zoom call because no one sees them. Stage 2. Sweats are okay for grocery store shopping. Stage 3. Sweats okay for every single event in life. Is there a stage 4? Sweats need never be washed. I'm sorry, I just thought that was cute.
That's almost accurate.
Yeah, you know, I mean, you may not like this meme, but I thought it was kind of cute. So there you go. All right. Are you guys still alive or what?
Yeah, we're
Yes.
live.
Yeah, I'm still here.
It's time for a poll. All right. Let's see. Let me go look for something. Okay, let's do this one. Are you Star Trek or Star Wars? Vote now. Voting is in process right now. Okay, you guys still out there? We're voting. Are you Star Trek or Star Wars? Or maybe you can't decide. You got to go both. I don't know. Or maybe you can't stand sci-fi. Yeah? Okay, let's check it out. Ooh, boy, you're going to be surprised about these results, people. Check it out. Star Trek is the least. Oh, man. Star Wars is the most. Sci-fi, yuck. And some of you are both. Well, congratulations to all who voted. You're more of a superhero guy. Okay, I get it, Luke. Yeah, forget this Star Wars stuff. I mean, do any of you folks watch Mandalorian? Yes, no? Go to the participants and yes or no if you vote.
I did.
Okay, vote yes. Are you a Mandalorian person? I haven't seen it at all. I don't know if it's good or not. Mandalorian, any good?
Pretty good,
Pretty
honestly.
good. Worth seeing. Planning to? Yeah.
Yeah.
I don't know. So it looks like some of you are not really voting. All right. Anyway, back to reality. Okay. So how do we get the curvature of a parabola, which is not constant? We saw in the very beginning here when we were talking about curvature that a parabola can be more curvy at its vertex than it is at other locations on the parabola. Fine. And if you graph this two-dimensional vector value function using parametric mode on your calculator, you will find it is indeed a sideways parabola. Okay? In fact, I think I have a picture of it down here. No, I don't have a picture of it down here. Never mind. Okay, so let's take a look at how you would get this. Now, I'm going to tell you a full disclosure. This formula for curvature that we used in the last 3 examples is doable, but it's going to take you a long time because you're going to get some really nasty looking derivatives, quotient rule. It's going to take you a while. I used to do this in my lectures, but I've decided it takes too long. So it's going to turn out that the curvature is going to be found much easier using that other formula, since T and T prime are going to be a challenge. And by challenge, I mean it's going to take a long time to get those derivatives, quotient rule and all that other stuff. Terrible. Let's use a different formula for curvature. And you can, because there's different ones. We're going to do the cross product of velocity with acceleration's magnitude, and then we'll divide by speed getting cubed. I know that is a wacky curvature formula, but it works. So to use this formula, we're going to have to go get r prime and r double prime. Okay, so r prime is pretty easy, 2t 0, 1. And notice the j is missing. That's what we have there. And then your acceleration vector, our double prime, ooh, it's going to be a constant vector, 2, 0, 0. Nice. So if you're going to take the cross product of these two puppies like so, and some of you are not using the correct 3 by 3 determinant. See these bars that I have on the left and right hand sides? They're all the way. Like some of you are being really cheap. You're like going, oh, I'm only going to put the bars down below. No, 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 no. You do the whole shebangy, okay? You'll see in linear. Otherwise, I'm going to start docking you points for doing lousy. This is supposed to be 2, 0, 0. Okay, so when you do this 2 by 2 or 3 by 3 determinant method, you're going to end up with 0 for your first component. You'll end up with 2 for the second component. And believe it or not, you'll get 0 for the last component. There's your cross product. Great. And so what is the magnitude of this? Well, it should be obvious. You know, square root of 2 squared is going to be 2. Fine. And then we know that the denominator for the curvature was the magnitude of speed. So for us, that's going to be 2t squared plus 0 squared plus 1 squared, which is square root of 4t squared plus 1. And so your curvature is going to be the magnitude of the cross product, which we got as 2, all over the speed getting cubed. I know this is like wacky. And that's it, pretty much. Now, when does a max occur? Like, when is this curvature maximized? The max occurs when time t is equal to 0, because that's when that fraction on the bottom is going to be the smallest. And that occurs at the point on the curve when you plug time t equals 0 into your original position vector. That occurs at the point 0, 0, 0, essentially. Okay. So if you graphed this curve and it turns out it's in the XZ plane, so I should say XZ plane is where this thing is, this thing anyway, it would be sitting in the XZ plane. Okay, I'm done with that. I do want to say that when you get, when t is equal to 0, k will be 2. And so if you did look at this parabola we're graphing, I want to show you something. If you were to snuggle a circle in this, and what do I mean by snuggling a circle right there at the vertex? Like, here's your vertex. If you were to snuggle a circle right there, the circle would have radius 1/2, because remember, curvature and the radius of a circle are inversely related. So this would be a half circle, and it would snuggle in there. And that circle is known as an osculating curve or osculating circle. Okay. So I'm going to do this next example here. When we do a curvature of another parabola, y equals ln of x. Is that really a parabola? Well, it is. It's sort of like, it's kind of a sideways one that's really fat. You can think of that as a big old parabola, kind of rotate it a little bit. So we're going to find the curvature k for that. Okay. So I'm not having you do any problems on today because they just take too long, but I hope you can appreciate that this is pretty formulaic stuff. Things will start heating up on Friday. We're winding down the vector valued function stuff today. And it is kind of like, curvature. Okay. So this osculating circle, we're going to do another one in the next problem. And it's a circle passing through your point with a radius that's 1/k that kind of fits in on the concave side of your curve. I like to think of it as snuggling in there, that shares that common tangent line with your curve at that point where it's snuggling. So what we're going to try to do with this y equals ln of x curve is we're going to try to snuggle a circle in here, you know, like right here, like that. And so that's our goal. That's going to be that osculating circle. So first, and that's when x is equal to 1. So when x is equal to 1, this point is 1, and then ln of 1, which is 0. So 1, 0 right here. Let's put it right here. Okay, so that's our goal for this wacky curve. Let's do it. So here's a different k that we're going to use. We're going to use k equals the second derivative's absolute value divided by 1 plus y prime squared to the 3/2. What? That's another curvature formula? Yep, I gave you a whole bunch. Well, how do you know you use this one for this problem? Because this is one of these two-dimensional problems where they're giving you y a function of x. So that's how you know. So let's go get all the ingredients. So what do I mean? Well, you're going to need to get y prime, and the derivative of ln x is 1 over x, which is x to the -1. Then you're going to need y double prime, okay? And that's going to turn out to be -1 x to the -2, and I rewrite in positive exponents, I get that, fine. Now what? Your curvature is going to be the absolute value of your second derivative. I know this is going to look pretty gross. Divided by 1 plus your first derivative, 1 over x getting squared, raised to the 3/2 power. That is just nuts. Okay. Now, if you evaluate at x equals 1, then your curvature is going to be absolute value of -1 over 1, which is 1. And then you'll have 1 plus 1 over 1 to the 3/2. And this is going to be 1 all over 2 to the 3/2 power, which is a constant. Okay. So what does that mean? That means that the osculating circle, the snuggle circle, that's not a technical term, okay? That's just my speak, is going to have a radius that's 1 over k. So that for us, that's going to be 2 to the 3/2 is going to be the radius of this snuggle circle, which is the same as 2√2. Okay, fine. Now, when you snuggle this circle in here, like, oh, okay, here he is, like, oh, the question is, what is the center point? You know, that's going to be a little bit tricky because, and this is the whole plan. This is a little bit of a hard problem. When I first saw this, I went, are you kidding me? But it's actually real. I hope that you can appreciate that if you draw a tangent line to the curve right there when x is equal to 1, it looks like that. And if you draw a line that's perpendicular to that tangent line, this center point of your circle is going to be on the perpendicular line, where the distance between the center and that tangent point is this radius here. Eee, okay. Wow, that's just nuts. Okay. Why is that going to help us? So here's the plan. I don't know what the center point is. I'm going to just put coordinates x, y. But I do know the distance between x, y and the point 1, 0. So here's what I do know. I'm going to start using the distance formula. I need another piece of paper. So if you look at my picture here, this distance d is, and you guys know the distance between 2 points in the plane, it's the square root of the sum of the squares. So you don't know what x and y are. So just take the difference of the x coordinates and takes the difference of the y coordinates and set this equal to 2√2. And so, and it's like, oh my God, you're kidding me. So what do you know about y? So I'm going to save this for the moment, save this formula for the moment because you're not ready yet. Let's go get the tangent line. Here's the tangent line. You did this in Calc 1. Do you remember finding tangent line equation? So the tangent line equation is y minus the y coordinate of the point we're trying to find, so 0, equals, you know, m times x minus 1, but m is f prime of 1, which we already got. F prime of 1 is 1 over 1, which is 1. So the tangent line has this equation, y equals x minus 1. This is the tangent line. So how do you get a line that's perpendicular? Do you guys remember that lines that are perpendicular have slopes that when you multiply the slope of your line with the other slope, you get -1? So this guy's slope is 1. So the slope of a perpendicular line will be -1. Yeah. So what? So we're going to call this the normal line or the perpendicular line equation. He still has a point 1, 0 on the line, but his slope m is -1. And so then when you distribute your negative, the perpendicular line or the normal line equation is that. Okay, so how is that helpful? Well, if you go back to the picture, the center of this snuggling circle lives on this normal line. This is the normal line. So what does that mean? So this value of y that we got, y equals -x plus 1, you're going to plug this into the distance formula that you have right where I said save for later. Are you kidding me? No, I'm not. So like right here, where there's a y, since the y that we're dealing with, which is the y center of the circle, your distance, which is square root of x minus 1 squared plus, and then what you're going to do in place of the y, you're going to put -x plus 1 and then square. This better equal 2 root 2. So I claim that this 1 minus x squared is the same as x minus 1 squared. So these are like terms, and you can add them together. 1 apple plus 1 apple is 2 apples. And that equals 2 root 2. And we're trying to solve for x. We're almost done. So then what? Well, you can rewrite this as square root of 2 times square root of x minus 1 squared. And over here you have 2 root 2. So right now we can divide out by root 2, both sides, like that. And you get, the left-hand side is just going to be x minus 1. And that's equal to 2. Add 1 to both sides and you get x equals 3. Good news. I have the x coordinate of our circle, the snuggle circle. That's the x coordinate of the center, or the osculating circle. So how do you get y? Well, you know that y is going to be on a normal line. So we'll use the normal line equation and substitute x equals 3. So the y coordinate of this osculating circle is -2. So the center of the circle has coordinates 3, -2. Finally. Now what? Well, you can actually write your equation of your circle now, because you guys know equations of circles. The standard form is x minus the x coordinate of your center plus y minus -2 is equal to your radius squared. And I think this is 8. And so this is the equation of your osculating circle. And if you're like, oh my God, that was intense. It wasn't intense so much of the calculus, some of the geometry, trying to come up with it. But hey, if you're an engineer type, that was exciting. Okay, so I'm just going to finish today's lecture by alluding to something that our physics brethren find very, very key. There's this idea of acceleration, the acceleration vector, which is r double prime. It can be proven to lie in the same plane as the t and the n vectors. It's, you know, your unit tangent vector and your principal normal vector. He is guaranteed to lie in that plane containing the t and n vectors. And so I'm not going to get too much into this because I don't have time. But I do want to say that when you are working in physics, because of the fact that t and n lie in some plane here, here's t and here's n, remember they are orthogonal to each other, you can write your a as a linear combination of t and n. Instead of the I and j vectors, say, you can resolve a into this linear combination of some weird coefficient here times your unit tangent vector plus some other weird coefficient times your unit normal vector. And folks, linear algebra people do this all the time because they do something called changing bases. I don't want to get into that so much now, but the a sub t, which is known as the tangential component of your acceleration, it is has something to do or related to the rate of change of speed. And your normal component is a function of both speed and curvature. So some of these concepts you've already learned with me, and you can easily study them on your own a little bit more. But it does start looking pretty gross. Like your a sub t you have two choices. If you are using the arc length parameter to parameterize your function, and remember, that's very special, you can quickly find your a sub t by taking the second derivative of your vector valued function, or you have to do this dot product of the velocity and acceleration vector divided by the speed. And then your a sub n is you can use one of those formulas, whichever one's easy. Okay. So I'm going to end it there. I think that's a good place to quit. I'm not going to test you on this a sub t, a sub n. If I might have thrown in a homework problem or two just for kicks and giggles, but I didn't put it on any quizzes or exams. Okay, so it won't be on Sunday's quiz. Though curvature will, and so will arc length parameter and arc length. So those things are key.